Hello everyone, welcome to Chemical Reaction Engineering Laboratory. We are here to understand about combined flow reactors. So let's go to our setup. So our setup for today's experiment, the combined flow reactor, is here as follows. Today, we are going to dive into the world of combined flow reactors, the versatile tools at the heart of many chemical and industrial processes. In this video, we will be discussing about the chemical reaction taking place between ethyl acetate and NaOH in this reactor, and we will be understanding about various chemical reaction kinetics as well as conversion and various other phenomena related to this experiment. So, let's get started. Hello, welcome. Today, we are diving into the fascinating world of combined flow reactors, versatile tools at the heart of many chemical and industrial processes. In this video, we'll explore how these reactors blend the principles of both plug flow as well as continuous stirred tank reactors to optimize reaction efficiency and control. Whether you are in chemical engineering, process design, or any other industry, or curious about the industrial chemistry, we'll break down how combined flow reactors achieve higher yields under complex reactions and adapt to diverse applications. So, let's get started. Chemical reaction engineering is a core field within chemical engineering that focuses on understanding, designing, and optimizing chemical reactions and reaction systems to produce desired products efficiently, safely, and sustainably. It is important as it spans various areas of interest like optimizing production efficiency, designing safe and sustainable processes and industries, scalability from laboratory to industrial processes, and developing new products and technologies. Let us now discuss about one of the most important components of any chemical process, the reactor. Reactors act as controlled environments where chemical processes and reactions take place efficiently and safely. Their importance lies in optimizing the reaction rates, maximizing production yields, and ensuring precise control over conditions such as temperature, pressure, and concentration. Reactors are used in various industries, from pharmaceuticals to petrochemicals, allowing the production of essential products, fuels, plastics, and medicines on a large scale. There are several types of reactors, each designed to suit specific reactions and operation needs. Let us have a look at each one of them. Very first is batch reactor. These are closed systems where reactants are loaded and the reaction is allowed to proceed without further input until completion. They are commonly used in small-scale production, pharmaceutical industries, and research labs for precise control over reaction conditions. The next type is a continuous stirred tank reactor. In a CSCR, the reactants are continuously fed to the reactor, while products are simultaneously removed, ensuring a steady-state condition. CSTRs are ideal for reactions requiring constant mixing and are widely used in industry for reactions with moderate reaction times. The third type is a plug flow reactors, or CFRs. The reactant flow to a tubular reactor and each plug of reactant reacts as it moves along its length. This reactor type is efficient for high thorough reactions with fast kinetics and is often used in large-scale industrial processes like polymerization and gas-phase reactions. The next type are the packed-fed reactors. These reactors are filled with catalyst particles and reactants flow through the pipe, allowing the catalytic reactions to occur. They are commonly used in catalytic processes such as petroleum refining and environmental treatment. The packed pipe used in this, the packets they increase the surface area for reaction due to which our conversion increases. The next type and the final type of reactors in our case are fluidized bed reactors. In these reactors, a solid catalyst is suspended by an upward flow of reactant, enhancing mixing and reaction rates. They are used in processes requiring high heat and mixing, such as production.
Hello guys, so here we'll be discussing about what a PFR is, how they work, what they are commonly used for, and also develop an equation for them. PFR stands for plug flow reactor. Much like CSTRs, PFR also operate continuously, meaning they are a steady state process. PFRs are commonly a long coiling tube in which there is a reacting component. Commonly, we will also have a heating or cooling jacket around the reactor to manage the temperature of the system. Which of the two jackets is used generally depends on the reaction occurring, like whether it is exothermic or endothermic. In these types of reactor, there is just one inlet and one outlet, and as the reactant works, it weighs throughout the reactor. Continuously the product forms, and therefore the concentration of reactant decreases along the length of the reactor. There are many ideal assumptions with the plug flow reactor. So let's go through them now. Firstly, we assume that there is no axial mixing. That means we are assuming that point B has no interaction with points A and C. Secondly, and the reason for our first assumption is that we assume perfect radial mixing, which means if we were to take a cross section at any point in our ideal plug flow reactor, then we would have the exact same composition and temperature throughout the entire cross section. Hence, therefore, because of these two assumptions, we track that the changes in our fluid composition are a function of distance throughout the plug flow rather than a function of time, which generally happens in batch, semi-batch or CS. So, our plug flow reactor is a steady state reactor. That means that when operating, we will continuously be feeding it reactants and removing products at the same rate. The idea here being that the new reactants enter our tank, stay reacting for a certain amount of time, which is called the residence time, and then leave the reactor once the reactant has become a product. Hence, here we should note about the residence time of a PFR is slightly different from a CSTR's residence time. In a CSTR, the residence time is a distribution based on statistic, and that is why it looks like a bell curve. It is based on average time a particle spends in the CSTR. Whereas in a PFR, we have just a single residence time, as we are assuming that the fluid is continually and always moving forward at a constant rate. This is why we call it a plug flow reactor. Now let us discuss some of the advantages of PFRs, as they are generally great for gas phase and liquid phase reactions. Additionally, we can experience fast reaction times in plug flow reactors, and therefore we have higher levels of conversions for the volume needed, unlike CSTRs. So also, operating continuously is great for industrial scale-up of a reactor, like batch and semi-batch reactors, which is harder to scale as compared to plug flow reactors. We can also achieve higher temperatures in PFRs, which is sometimes necessary for reactions. Another benefit is that we have low labor cost, as the reactor will mostly be running itself as it is steady state. However, it is just a long tube reactor. Cleaning the PFR can be a challenge to make sure that it is properly sanitized upon shutdown. So now we will be studying about CSTRs. In particular, we'll talk how they work, what they are commonly used for, and develop an equation for them. CSTR stands for Continuous Stirred Tank Reactor. Unlike our previous semi-batch reactors where it was not in a continuous mode, which also refers that our reactors are steady state. Well, does a CSTR look like? CSTRs are commonly just a tank. This could be small like a pilot plant or very large for an industrial setting. In this tank, there are some stirring apparatus that moves and agitates the fluid within the reactor to promote better mixing, as there are tons of designs for the stirrer many of which are best for a given situation. However, this is not important, as we may be considering what future designs could be for a reactor. Additionally, there could be several inlets feeding the reactor and an outlet to remove the reacted product. CSTR are one of those few ideal reactors which are generally used in the industry because of their simplified use. CSTR have few associated ideal assumptions, and now let us talk about them. Firstly, we have nothing changing in time since we are at a steady state. Now, realistically, when we begin a reactor, there will be a period where we are not at the steady state. This is known as the transient portion or the transient region. You can imagine this through the change in concentration of a reaction product. However, when we are analyzing CSTRs, we are more often than not just interested in the region that is not changing in time. A second assumption about CSTRs are that they are perfectly mixed. This means that the mixture within the CSTR is so well mixed that the composition, temperature and other characteristics of the mass anywhere within this reactor will give us the same results. So, because of our CSTR is at a steady state reactor, that means that when operating, we will continuously be feeding it reactants and removing products at the same rate. The idea here being that new reactants enter our tank, stay for a certain period. This is called the residence time. How long a particular particle will stay within our reactor and then leave a reactor once the reactant has become a product. Let's discuss about the cons or the disadvantages of CSTRs. Firstly, the CSTRs are not great with viscous fluids, and this makes sense. Like, just imagine we had something super viscous. So the agitator would have a very hard time moving that fluid, and therefore our well mixed assumption is just invalid, or we would need a very powerful motor and a strong paddle to shear the viscous fluid. Additionally, it is also known that the conversion of a reactant in CSTR is not as volume efficient as some other reactors. Therefore, we may need a larger reactor to ensure that our reactants are sufficiently reacting to become products in terms of industrial use. These type of reactors are commonly found in industries where less viscous fluids are used and where a steady state is ideal, such as wastewater treatment facilities, fermentation, or some other multi-processes. And finally, we have introduced the mole balance like we did in PFR. So here, a general mole balance has been written and a general design equation for the CSTR has been derived. So have a look at it. As I mentioned earlier, the combined flow reactor consists of both plug flow as well as mixed flow reactor arranged in series. So we will be discussing what are the various advantages, like what kind of conversion takes place for different kind of setups, like when we have 2 PFRs in series or 2 MFRs in series or 1 plug flow and 1 mixed flow reactor in series in upcoming minutes. Let's discuss about the cons or the disadvantages of CSTRs. Firstly, the CSTRs are not great with viscous fluids, and this makes sense. Like, just imagine we had something super viscous. So the agitator would have a very hard time moving that fluid, and therefore our well mixed assumption is just invalid, or we would need a very powerful motor and a strong paddle to shear the viscous fluid. Additionally, it is also known that the conversion of a reactant in CSTR is not as volume efficient as some other reactors. Therefore, we may need a larger reactor to ensure that our reactants are sufficiently reacting to become products in terms of industrial use. These type of reactors are commonly found in industries where less viscous fluids are used and where a steady state is ideal, such as wastewater treatment facilities, fermentation, or some other multi-processes. And finally, we have introduced the mole balance like we did in PFR. So here, a general mole balance has been written and a general design equation for the CSTR has been derived. So have a look at it. As I mentioned earlier, the combined flow reactor consists of both plug flow as well as mixed flow reactor arranged in series. So we will be discussing what are the various advantages, like what kind of conversion takes place for different kind of setups, like when we have two PFRs in series or two MFRs in series, or one plug flow and one mixed flow reactor in series, in upcoming minutes.
After understanding about plug flow and mixed flow reactor, now let's talk about conversion. Conversion to chemical reactions is a measure of extent to which reactants are transformed into products. It is typically defined as a fraction of percentage of the initial reactant that is reacted in the reaction. For example, if a reaction consists of 100 moles of reactant and by the end of the reaction 80 moles of products is formed, then the conversion is 80%. Here's a comparison of conversion for two different configurations, that is, two mixed reactors in series, or two plug flow reactors in series, or one mixed flow and one plug flow reactor in series. These reactors handle the same reaction type, same total volume, and reactor concentration. So, we can directly compare the conversion efficiency. The setup, which is two mixed flow reactors in series. When two MFRs are placed in series, the conversion is compared to a single MFR of the same total volume. The first reactor will partially convert the reactors, reducing the concentration that enters the second reactor, which further increases the conversion. However, since MFRs maintain a uniform concentration, the conversion still won't reach the levels that can be achieved in a PFR series under similar conditions. Hence, the conversion in this case is moderate, higher than single MFR, but still lower than PFR for higher order reactions. Let us understand the second type, which is two plug flow reactors in series. Placing two PFRs in series is equivalent to single PFR with same total volume, because each segment of a PFR continuously processes reactants without partners. Since concentration gradually decreases along the length of each PFR, this arrangement maximizes the reaction rate along the reactor length. Since concentration gradually decreases, now as PFR takes the advantage of concentration rate. Now let us look at the third type, which is one plug flow reactor followed by one mixed flow reactor in series. In this arrangement, the PFR partially converts the reactor, reducing its concentration before it enters the mixed flow reactor. The MFR then provides additional conversion at a lower reactant concentration level. The overall conversion will be lower than 2 PFR in series, but generally higher than 2 MFR in series, as the initial PFR benefits from the higher concentration at the start of the reaction. The conversion in this case is intermediate and higher than 2 MFRs in series, but lower than 2 plug flow reactors in series. Now, after understanding briefly about the theory and production of our experiment, now let's move forward to understanding the materials that are used and the reaction mechanism and various reactions along with chemicals which are taking part in this experiment. Let's go.
Everyone, today we are going to demonstrate a combined flow reactor experiment. This experiment helps us understand reaction kinetics by observing how two chemical solution mix and react in a flow system. Material required for this experiment, we will need the following materials. Firstly, two conical flasks. This will hold our chemicals for the initial setup. Two beakers for transferring the solution to the flask and ensuring we measure the right amount. Burette with stand. The burette will control the flow of one solution into the another. 50 ml of measuring cylinder for accurate measurement of our liquid chemicals. Chemicals we will use that are sodium hydroxide, that is of 0.1 normality, hydrochloric acid, that of 0.1 normality, and phenolphthalein indicator. This will help us virtually track the reaction as it changes color at different pH levels. So let's move to the other part. So let's talk about the chemicals that are used in the combined flow reactor and what are the role of these chemicals. So let's talk about sodium hydroxide. This is our basic solution and it will react with the acid to produce the water and salt. Second is hydrochloric acid of 0.1 normality. This is acidic solution that will react with NaOH. And third one is phenolphthalein indicator. As it is indicator, it will change the color of the chemicals that we got sample from the combined flow reactor. So there is one question there that why we are using only phenolphthalein indicator, why we are not using any other indicator. So let's talk about its importance and why we are using only specific specific chemical, that is phenolphthalein indicator. So let's get started. So we use phenolphthalein as an indicator because of its clear and distinct color change in the pH range where our reaction occurs, which is an ideal for neutralization reactions between an acid and base. Acid, that is HCl, and base, that is NaOH. Okay. Now phenolphthalein is a colorless in acidic condition, that is its pH will be less than 8.2, but turn pink in basic condition, that is pH is greater than 8.2. This makes it perfect for monitoring the reaction progress visually. So when we add HCl to the NaOH solution containing phenolphthalein, the pink color fades as the base NaOH neutralizes. So indicating the shift from a basic to a neutral or slightly acidic environment. Okay. Other indicator also may change the color at different pH range, which might not show as a clear transition or may not visually distinct for this specific experiment. Not in only a specific experiment, but in all experiments we are using a phenolphthalein as an indicator only because it is it create a more clear, it show a more clear color, and what we are able to find that we get through the phenolphthalein indicator. So let's move to the next part. So as in discussed previously video, that our aim is to determine conversion in both reactor for saponification of ethyl acetate with NaOH at ambient temperature condition. So let's explore the reaction of ethyl acetate with NaOH and let's see what the products we are getting. So let's get started. Hello everyone. Today we will be exploring the reaction between ethyl acetate and NaOH in a combined flow reactor. This experiment is a great way to study a chemical reaction kinetics and to understand how reaction proceed over time. I will walk you through the what this reaction tells us and behavior of chemical reaction in the flow system and key conclusion we can draw. So let's start. So ethyl acetate reacts with sodium hydroxide, a strong base, is in a reaction called saponification or hydrolysis. In this reaction, ethyl acetate break down into in the presence of NaOH to form sodium acetate and ethanol. So this is second order reaction since the rate depends upon the concentration of both ethyl acetate and NaOH, sodium hydroxide, that is. So what is the purpose of using this chemical in a combined flow reactor? This is the question it is. So I'm telling you answer that a combined flow reactor allow us to study a reaction in a continuous flow system. Unlike a batch reactor where reactors are mixed once and allowed to react over time, a combined flow reactor involves the continuous introduction of a reactant and removal of the products. Continuously reactants are coming, products are coming outside. So when we want to take a sample of any reactant, so once we have to stop the flow of other reactant and take the reactor of that whatever we want to sample, take the of the reactant. So a combined flow reaction involves the continuous introduction of reactant and removal of the product. This setup in industrial process help us understand the flow reaction behave in flow system such as in chemical manufacturing or water treatment. So as the reaction between the ethyl acetate and NaOH take place, following changes can be observed. That is for concentration changes, and second one is pH changes. So first one is concentration changes. Discuss about concentration changes. By monitoring the concentration of ethyl acetate or sodium hydroxide over time, we can observe that the rate at which the reaction proceeds. We can observe the rate at which the reaction proceeds. Means when the reactions are started between the ethyl acetate and NaOH, we can easily determine the rate of the reaction. The concentration of reactant decreases over time, which directly impacts the reaction rate. And second one is pH change. As NaOH is consumed in the reaction, the solution becomes less basic. This change in pH can be an indicator of reaction progress, showing us how much of the reactant has been used up at a given time. So one of the primary goal of experiment is to determine the reaction rate graph. For this reaction, we get a reaction rate that is equal to K CS3 COO CS2 CS3 in one bracket, and in another bracket it will NaOH, where K is a rate constant and the reaction rate depend on the concentration of both ethyl acetate and NaOH, because it is a second order reaction. So its concentration obviously depend on the both reactions. By measuring this concentration over time, we can calculate the rate constant K, that is K, which give us quantitative measure of how fast the reaction occurs under a specific condition. So what I have talked, let's conclude in a summary, is that in the reaction between ethyl acetate and sodium hydroxide in a combined flow reactor offer valuable insight that are reaction rate, kinetics analysis, real world application. That is, under this reaction is not only academically interested but also has a real world application. Saponification reaction like this one are important in the production of soap, biodiesel and other chemical processes. This will play a major role in the industrial process. Now it is very important as in industry also. So now let's discuss the mechanism of the reaction. So let's begin the mechanism of the reaction. So let's start a mechanism. The mechanism of ethyl acetate and NaOH, how they are reacting and what product they are forming. Let's get started and understand step by step. Before going into detail about the mechanism, let's understand what this reaction is about and why ethyl acetate, which is an ester, react with sodium hydroxide, which is a strong base, and forming a two new product, that is sodium acetate, that is a salt, and ethanol, that is a alcohol. So let's break down it into a step by step and see what is happening in the mechanism and how the products are forming. So let's get started. So in a mechanism, firstly there will be a nucleophilic attack will be there. The first thing that happens in the reaction is an attack of an hydroxide oil, that is OH negative. So sodium hydroxide is split into Na positive and OH negative in water, and the hydroxide ion is very reactive because it has a lot of electrons. Secondly, in ethyl acetate there is a carbonyl group, that is C double bond O, which is a carbon atom double bonded to an oxygen atoms. The carbon in this group is partially positive, means it's looking to accept an electrons, and the OH ion that is negative attack the carbon, breaking the double bond and forming a temporary compound. At this point, the molecule is unstable and quickly moves to a next step. That is, next step is the formation of tetrahedral intermediate. Now let's look at what happens after attack. The carbon and the carbon that was attacked by OH negative now has four groups attached to it, forming what we call a tetrahedral intermediate. Means the product that is forming, that is a tetrahedral intermediate. And the structure that they are forming is not stable because the molecule is holding too much charge and want to stabilize itself, so it rearranges. So in third step, what will going to happen, that is breakdown of the intermediate, because the compound that is formed in second step, that is big compound, and the carbon doesn't hold such big compound. So in third step, what we are doing, we are breaking into a small group so that carbon can easily hold the atoms. So third one is breakdown of the intermediate. In this step, the intermediate rearranges to form more stable products. The oxygen from the original carbonyl group reforms the double bond with the carbon, and at the same time ethyl group, that is CH2 CH3, get kicked out. That means it will replace out as a separate part called ethoxide ion, that is CH3 CH2 O negative. Now we have a new structure, that is sodium acetate, and that we call CH3CO negative, but we are not done it because ethoxide ion is still floating around. So in final product, what we can do, formation of a final product. In final step, ethoxide ion, that is CH3CH2 negative, reacts with water or a hydrogen source in the solution to form a ethanol, that is CH3CH2OH. Remaining part of molecule become sodium acetate, that is CH3CuNO, and reaction is complete, and now we have two stable products, sodium acetate and ethanol, and that's what we want by the help of mechanism. I hope whatever I discussed you got it, and mechanisms, and we study mechanism for better understanding of the reactions, that actually how they are forming a product from after breaking, a lot of steps involved, and we are using this reactions, and we are using this chemical in a combined flow reactor because it is a straightforward reaction. There is not a very much complex step involved in this reaction. It is totally a straightforward reaction. So that's why we are using a simple reaction. It is well-known reactions. In every experiment, whatever experiment we have performed in the laboratory, we are using the same reaction again and again, because it is so simple to understand, and its mechanism also so simple. Only 3 steps involved to form new products. Now let's discuss about other parts of the reactions. So now talk about some experimental finding that are found during the experiments. If we talk about the reaction between ethyl acetate and NOH, that is sodium hydroxide, by experimental finding, we came to see that it produces activation energy of 29.775 kilojoule per mole. This amount of activation energy it produces during the reactions. And second point is, it is a slightly exothermic reaction. It means that it can produce some amount of energy during the process. Now we have a question that why we are using same base, that is NOH with ethyl acetate. Why we are not using other base with ethyl acetate? And there is some other base also which we can use to ethyl acetate to get the desired product. Some bases are that potassium hydroxide, calcium hydroxide, and lithium hydroxide. Some more bases are there. So just for the sake of your knowledge, I am telling just 3 bases. Some more bases are also available. Experimentally, by researchers, they came to conclusion that NOH in comparison to other bases, when reacted with ethyl acetate, it produces a 37% yield. 37%, approximately 37% yield after 1 hour at 55 degrees Celsius, making it more effective base for these reactions. Means if we consider ethyl acetate and if we consider other base, for example potassium hydroxide. So when you compare potassium hydroxide and NOH, you came to see across that NOH produces high yield in comparison to potassium hydroxide. It means we have to use such type of base that can produce high yield in less time, and it also consumes a less amount of energy in comparison to other bases. So these all things has been experimentally concluded. Okay, thank you. One question raises in our mind that why we are always using the ethyl acetate NOH in the laboratory, because whatever experiment we have performed, we have seen that we are using the same reaction again and again in each and every experiment. So what is the reason behind it? So let me explain you. So let's start with primary reason. That's why we are using a ethyl acetate and NOH in each and every experiment. The primary reason we use ethyl acetate and sodium hydroxide is for saponification reactions. It means reaction involves hydrolysis of ester, where the ethyl acetate react with sodium hydroxide to produce ethanol and sodium acetate. This is the primary reason to use sodium acetate and NOH in the laboratory. Now move forward to a second point, that is controlled reaction environment. So in this, when we are using sodium hydroxide, provide us a controlled reaction, controlled basic environment that enhance the reaction rate. And the strong alkaline nature of sodium hydroxide helps to break down the ester bond in ethyl acetate more effectively than weaker base. This lead more efficient saponification process, which is a critical when we used precise result in our experiment. Now let's move forward to kinetics studies. In our laboratory, we often conduct kinetic studies to understand different factors affecting the rate of the reactions. Ethyl acetate and sodium hydroxide are chosen because they allow us to easily monitor changes in the concentration over time. By measuring how quickly the reactants are converted into products, we can derive important kinetic parameters such as reaction rate and rate constant, reaction order and rate constant. These are important parameter under the kinetics of the experiment. Now let's move on to safety and handling. Both chemicals are relatively safe to handle when laboratory protocols are followed. Ethyl acetate has low toxicity compared to other organic solvents, making it a preferred choice for many applications. Sodium hydroxide can be managed safely without appropriate equipment like gloves and goggles. NOH, sodium hydroxide, is widely used in the experiment because it doesn't have any harmful effect. people are using it normally, and the reactions, and when both reactions are combining and they are producing a product, there is no any hazardous products is producing. It means it is safe to use. It has not any hazardous. It will don't impact any human beings, not even the environment. So these are the reason that why we are using the sodium hydroxide and ethyl acetate in our laboratory. Even in many other places we are using this type of chemical reactions. Yeah, thank you. Now let's move to
So let's get started. Today we will be conducting an experiment using both the continuous CFR reactor and the plug flow reactor. So let us better understand the chemical reactions in the different flow conditions. This is the foundational experiment in the chemical reaction engineering, showing how the different reactors influence the reaction rates and the conversions. We will take you through the entire procedure step by step. So let's get started. So let me introduce you with the various components of our experiment. So this is the flow rate tank. So here is the two rotameters which controls the flow rate, and here is the tank. Here is the reactant tank in which we are using here these components of our experiment. So one is ethyl acetate and one is ethyl. Here are the two rates that are given. So here there is a CFR reactor, here is a CSTR reactor. This is a controller through which we can operate. We can control the speed of the actuator and also on and off. This is the outlet from which we will take the sample. Our first step is preparing the 20 liters each of solution and wash and the ethyl acetate in the tank, which are the two reactors for our experiment. The exact concentration of each solution is crucial because the reaction rate and the conversion calculations depends only on time of initial conditions. So let us discuss some detailed explanation what we are reactors using in this experiment. So first understand the molarity. So molarity here represents the mole of the solute as per the solutions. So we need to prepare the solutions. We can do the calculations. The calculations will be shown in the calculation part so that we can calculate according to its molarity and of the both the components. So let's do it in a similar way for the ethyl acetate also. If the concentration specified, say 0.3 molar or 0.1 molar, follow the same steps to determine the amount of the ethyl acetate required. This is how we ensure the consistency in our experiment setup. Great. Now the solutions are ready and we are ready to perform an experiment. Now here is the step 2, that is adjusting the flow rates of the both the reactor. So we will set up the flow rates of our annualized ethyl acetate solution. Flow rate control is essential because at the time of the reactant stays near the reactor, affecting the conversion also. Understanding the flow rate and its importance. We control the contact time of the reactor, which influences how far the reaction progresses in each of the reactors. For instance, in the CFR, the reactants continuously mix with the content inside, while in the CFR, they flow into more orderly like the blood flow. Now, adjusting the flow rates of the rotameters. Now, adjusting the flow rates with the rotameter. Each rotameter ball allows us to regulate the flow of NaOH and ethyl acetate. We need to check the readings carefully and adjust slowly to avoid any overshoot. Now, step 3 is adjusting. The step 3 is achieving the steady state.
Once the flow rates are set, we wait for the reactors to reach the steady state. Steady state means that the concentration of the reactants and products inside the reactor have stabilized. We will now see why the steady state is required. In chemical reaction engineering, steady state conditions are the crucial. A steady state, the inflow rates of the reactor matches the outflow of the product, and the concentration profile don't change over the time. This makes us easier to analyze and compare the reactor's performance. This makes us easy to analyze the reaction comparisons so the next part is preparing the standard solutions for the titration. For the next part of our experiment, we need the two standard solutions, 0.1 normal of HCl and 0.1 normal of NaOH. This will be used in the titration step to determine the conversion rate of the reactor. Normality is the way to express the concentration that accounts for reactive capacity. For instance, 0.1 normal of HCl has the 0.1 equivalence of HCl per liter. Using the formula that M1 liter is equals to M2 liter to dilute the concentrated stock solution to the desired 0.1 normal. Similarly, we can prepare the NaOH solution also.
Now we have already saw the standard procedure of titration. Now proceeding towards titration of CSTR sample, that is post and at a workstation with a polygon class and a pivot. Simply, now that our standard solutions are ready, let's collect the sample from the CSTR and analyze the concentration of reactants. We'll do using a titration tube where a color change. Basically, going into details of explanation first, collecting the sample. We'll start by collecting 20 ml of the CSTR, which has achieved a steady state condition into a clean colloidal flux. Then, the endpoint of a titrate. Basically, going into details of explanation first, collecting the sample. We'll start by collecting 20 ml of the CSTR, which has achieved a steady state condition into a clean colloidal flux. Then, adding a 0.1 normal of HCl. To this sample, we'll add 20 ml of 0.1 normal of HCl and few drops of phenoxyl indicator. The indicator will turn pink in basic solution and become colorless in the acidic solution. Next, titrating with NaOH solution. Slowly, we'll add 0.1 normal of NaOH from the purine to the mixture, drop by drop, carefully. Observe the color change as this will indicate the endpoint. The amount of NaOH used will help us calculate the concentration of remaining NaOH in the sample. Now, cut to close up of titration process will explain the color change. Now, the next crucial step shall be to record the volume of NaOH used for future calculations, as it will allow us to determine the conversion rate in the CSTR. Now, titrating of the PFR sample, that is, now we'll take 20 ml of the sample from the PFR and repeat the titration steps. By comparing the results of CSTR and PFR, we'll get insights into how the dynamic influence of the reactions are getting up. Now, step 7 is the most crucial one, stopping the experiment and draining the reactors. Generally, now let's stop the experiment. First, close the rotameter valves of the. Now finally, let's stop the experiment. First, close the rotameter valves to stop the flow of the both solutions, and then drain each reactor through valve located beneath. Now, this cleanup steps ensures the reactors are ready for future experiments and helps maintain safety standards. Coming to the conclusion, and that's the complete run-through of the combined flow reactor experiment. Today we prepared the reacting solutions, set flows, reached steady state, and conducted titration by analyzing the titration results. We can compare the effectiveness of the CSTR and PFR reactor. Thank you for watching. I hope you found this tutorial helpful. If you have any questions or want more detailed explanation, please leave a comment. That will help us and help you too. Don't forget to subscribe for chemical reaction engineering content. See you next time. Bye.
So we have seen equipments like.
Now that we have discussed the experiment and completed the procedure, let's take a look at some of the conclusions we have drawn from this experiment. But before that, let's take a look at the result. As you can see, the result we have calculated the final concentration of the PFR and the rate constant of the reaction. And then we have calculated the final concentration at the outlet of MFR and the conversion. And similarly, we have also calculated the conversion of the overall system and also the PFR. Now, let's take a look at some of the conclusions we have drawn about the apparatus that are MFR and PFR. Combined flow reactor offers several advantages over the batch reactor. As you can see, the first of all is the overall conversion, where we can see the conversion of a single PFR or a batch reactor and compare that with the combined flow system. There is a clear difference. You can see that the combined flow reactor offers a large conversion over the single reactor systems, because the reactants stays a lot of time in the reactor and the residence time of the reactants in the reactor is large. That's why reactants get more time to react, and hence the conversion increases. Also, combined flow system offer much better heat transfer, mass transfer, and more precise control over reaction conditions, and potentially, of course, the overall high conversion. The saponification reaction proceeds efficiently in the combined flow reactor, and it proceeds with consistency and reproducibility compared to the batch processing system. The reactor design significantly increases the conversion and yield. Flow rate and residence time are important parameters for this experiment, as if you change the flow rate, the residence time of the reactants changes. Hence, the conversion and yield can subsequently change. Therefore, to achieve maximum efficiency and prevent incomplete conversion, these two parameters need to be kept in check. Comparing the conversion levels achieved in the combined reactor, those from the individual CSTR and PFR reactor, have now been concluded that they can achieve higher conversion. The combined flow reactor achieves higher conversion than a standalone CSTR, especially for reactions or conditions where we need a high conversion system. The combined flow reactor also take advantage of both plug flow and CSTR, hence leading to higher conversion even for certain higher order reactions.
Now, as we all know that if a reactant stays longer in a reactor, we know that they react more. And if we see the system, we can see that for the same flow rate in the combined flow system, the residence time is more as compared to the individual reactors, that is PFR and MFR, for the same flow rate. Hence, the conversion in the combined flow system is more than that individually in MFR and PFR.
Back mixing occurs when there is a portion of the reactant or product stream that is recirculated in the reactor. This recirculation causes a portion of the material that is already undergone some reaction to mix with the incoming fresh material. Now let's discuss that effect in the ideal PFR or CSTR. In ideal reactors like a plug flow reactor, material should move through the reactor without minimal mixing, ensuring that each portion of fluid experiences the same conditions, that is the temperature, concentration, etc. for the same amount of time. However, back mixing reduces the efficiency of this process in PFR. For the effect of back mixing in the MFR, that is the CSTR. Back mixing can cause due to turbulence, or it can be intentionally induced, which happens in the CSTR. In CSTR, by the way, this back mixing helps in proper distribution of the reactant in a more uniform way and also keeps the temperature steady. Now, if we come back to our experiment, we can clearly see in the CFR and MFR there can be a possibility of back mixing, especially in the CSTR section, which affects the conversion compared to an ideal PFR. Now, if back mixing is significant, it may reduce the conversion efficiency, particularly in higher order reactions. However, in some cases, mild back mixing can benefit reactions that proceed more effectively at lower concentrations. So we can finally conclude that the combined flow reaction system gives higher conversion than the standalone CSTR system. And also, optimizing residence time and understanding that kinetics can help us achieve the desired concentration. And we also studied the effect of the optimum residence time so that we can get a higher conversion value. This helps us understand both the reactor design and the reaction efficiency. Now let's move ahead with some discussion, like the saponification reactor in the CFR shows several interesting aspects in comparison with batch reactors. Like first of all, the continuous flow versus batch processing, where the continuous reactors often provide a more uniform reaction environment due to consistent mixing and residence time, which can lead to more efficient use of reagents and better control over the reaction rate. In contrast, the batch reactors might suffer from issues like temperature gradients or reagent depletion in certain zones.
If we compare the individual reactors, that is CFR and MFR, with the continuous combined flow reactor, we discuss about the residence time distribution. As you can see from this figure, the residence time distribution increases as we go from CFR to MFR. This residence time distribution shows us that there has been a proper mixing, and if we compare that to CFR and MFR individually at the same flow rate, then we might not find the same distribution. Also, the amount of time, residence time for the reaction might be less, hence the conversion might be low. And if you see from this, there can be, due to proper mixing, a more distributed curve for the system.
Third point is the scalability and efficiency of this reactor system. The CFR can be scaled to a large industry where a large amount of reactant needs to be treated at a minimum amount of time. Whereas in batch reactor, it is also very time consuming to react a large amount of reactants with the same efficiency as that of a CFR. In CFR, because of better mixing, a high conversion can be achieved, whereas in batch reactor the same cannot happen. Now the fourth point, the economic implications. While continuous reactors can be more efficient, their capital cost might be higher, and more complex controls might be required compared to a simple batch system. However, the potential for higher throughput and better product and better efficiency and reduced reaction time, this cost can justify in industrial applications. The fifth point is the future goal. That is, what can be done in future to further optimize the reaction design, exploring different configurations or materials for this system, or also think about the incorporating catalyst or other additives to increase the reaction rate or selectivity, and also to increase the conversion of the reactions. So that's all for this video. We have discussed about the MFR, TFR, the mixed flow system, that is this combined flow system, and also about the chemicals used in this experiment. And we have also demonstrated the procedure of this experiment. And finally, the results. Thank you.
As you can see, this is the resulting data we have obtained from this experiment. This is just a sample data we have obtained in 4 test runs. And if we take a look at the data corresponding to 5 liter per hour flow rate, the individual conversion of CFR, that is XA1, is 0.255, and the individual conversion of MFR, that is XA2, is 0.1409. But the overall conversion of the whole system is 0.36. So here we can see that the overall conversion is increased and more than the individual conversion of both the PFR and MFR.